All right. We're going to quantify how much stuff we can put into solution. We're going to use two terms for that generally. The first is just solubility. Now, solubility is usually mass of solute per volume of solvent. That's pretty easy. It's a mass and a volume. So we're looking at things like grams per milliliter. This can sometimes be just written as mass per volume, sometimes written as a percentage. That I've got this many grams as a percentage. Okay, so that gets to be a little bit troubling, but then you have to think, what's the density of water? What is the density of water? 1 gram per milliliter. So if I had 1 gram dissolved in, 1 gram of solute dissolved in 1 milliliter of water, that would be the same as 1 gram of water. Then I'd be able to figure out what my percentage was here. But usually we just go by grams and milliliters. Okay, this is just a good overall number, but it's not any use to us in terms of keeping track of stuff that's changing or going on in a reaction. In those cases, we're going to be talking about concentration. And concentration is moles of solutes, not mass, because mass, 10 grams of one compound is not equivalent to 10 grams of another compound, because the atoms have their own mass, right? This is the moles of solute per volume of solution. Ooh, this one's different. It's not solvent anymore. It's the finished product. Solutes and solvents are the two participants that make up the solution. Solute is a participant, but solution is the finished product. It's what you get at the end. So the wording here tells us something that we weren't thinking about. It tells us the procedure that this was made by. Okay. We have these things. I didn't bring one. I'll have to go back upstairs at some point and get one. They're called volumetric flasks. And they have a piece of glassware with a really long neck, and we put a stopper in the top here. And then the bottom part of it is kind of pear-shaped, okay? And there's a line etched into the glass. And that line tells you with precision, some of them are stamped, and it will tell you plus or minus 0.0 something milliliters. Tells you exactly what this volume is. Okay. So if I were to make a solution in this flask, what I would do is first weigh out a sample of it. And if I weighed out enough of it to be 1 mole of that material, then I would add it to the flask. So we start with the solid at the bottom of the flask. And then I would add enough water that I could dissolve it. And then carefully, I would add water all the way up until the meniscus of my solution touches that line. And if at that point I have 1 mole in 1 liter, let's say that this is a 1 liter volumetric flask. It's called a volumetric flask. okay, I would have 1 mole per liter, which is equivalent to 1 capital M molarity is moles of solute per liter of solution. Okay? When we working with molarity, it means you dissolve something and then dilute up to the final volume. If I did this wrong, I would get something else. There is another feasible way of doing this, which says, I know, hey, I'm supposed to dissolve this thing in a liter of water. Okay, so I could do that. I could take a volumetric flask and I could add a liter of water to it. And then I could take my solid and add my solid to that liter of water and turn it into a solution. I could do that. This would not be 1 mole per liter. Why would it not be?
Adding water afterward means that you're taking it up to 1
Yeah.
mole versus having it in a liter and adding more into it.
This started at exactly 1 liter. And then I added additional matter to it. This matter comes with a mass and a volume. So when I add this volume to this flask, the liquid layer is now all the way up to here. So it's not a mole in a liter anymore. Oops. The one on the left is called molarity. The one on the right, yes, you've done it wrong, but sometimes we have a use for this one. This is called molality with 2 L's versus the R. And molality is 1 mole of solute plus 1 liter of solvent. Okay. Now, the density of water is 1 gram per milliliter. How many milliliters are in a liter? 1,000. The answer is always 1,000. There are 1,000 milliliters in a liter. How many grams in a kilogram? 1,000. The answer is always 1,000. So 1 milliliter of water weighs 1 gram. How much does a liter weigh? 1,000 grams or a kilogram. So this is equivalent to 1 mole of solute in 1 kilogram of solvent. And by just changing that definition a little bit, I've just made this one useful. If I take a kilogram of water and I add my substance to it, this has a property that this one doesn't. You know how it was colder today than it was yesterday? And it's certainly colder than it was last week. What if the lab involved us making a solution and taking it out to the preserve, to the nature preserve, okay? Last week that was hot. This week it isn't. if I make this solution in the stockroom exactly up to 1 liter, and then I take it out into the hot sun for a full day's work, what happens to the volume of the liquid when it gets hot? They do what? No, I'm talking about the total volume that's inside. So we've already dissolved the thing in it. I'm going to take this liquid out and let it warm up ever so slightly. What happens to the volume? It goes up. Liquids and gases expand when they are warmed. And so now my volume might be here. Is this still a mole in 1 liter? No, because my volume changed. This one is sensitive to temperature. This one, the molality, the molal solution. I took 1 kilogram of water, I added a mole of substance to it, I took it out into the preserve. It also expanded because liquids expand when they get hot. Do I still have 1 mole of substance in this 1 kilogram? Yeah, the mass hasn't changed. The volume might have, but the mass has not changed. So this one does not change with temperature. That's the only reason we would ever use a molal solution in favor of a molar solution. As far as we're concerned, molarity is concentration. All of our concentrations will be measured in molarity, moles per liter, made up as molarity, solid first, solvent next. Okay, do a calculation. Let's do something. Let's make a solution and figure out how concentrated it is. So molarity, because it's dependent on volume, sensitive to temperature changes. Molality, because it's defined in terms of mass, is not temperature sensitive. Okay. Here's a question. Blank grams of blank were dissolved in blank milliliters. Nope. Nope. I'm going to change a single word. Up to. Not in, up to. That means I didn't take the volume and then add the solid to it. I took the solid and dissolved up to a number. What is the concentration of this solution? Okay. Give me a number. $20.20, or as the young kids say, 20.20 grams of, who's looking at me? What's your favorite metal on the periodic table? Taking a little bit too long with that. Iron. and an anion to go with it. There's something from the right-hand side of the periodic table, one of those anions that you had to learn. Pick one that you can guarantee will dissolve in water. Which anion's guaranteed to dissolve in water? Had a short list the other day. So first of all, we learned some anions, we learned some oxoanions. And then Monday we said, these are the solubility rules. This is always guaranteed to be soluble. Give me the one that's always guaranteed to be soluble. Potassium would be here. So on the left-hand side of the periodic table, it would be the metal.
Chlorine.
Most chlorides are soluble. Most of them. All nitrates are soluble. Okay. We're going to take 20 grams, 20.20 grams of iron nitrate, and we're going to dissolve them in water. How much water? Now think. 20 grams is going to be a fistful of material. If you want me to dissolve that in 3 milliliters of water, you can wish all you want to. It's not going to happen. So this needs to be a volume that is capable of diluting that, of accepting that. Pick a number. There you go. 250 milliliters of water. We need to know two things at this stage. We need to know moles equal. What does moles equal? What's the equation? Moles equals mass divided by formula mass. You need to work on that one. Should be coming to you quicker than this. And it asked for concentration. We're only interested in molarity. Molarity is moles per liter. Okay? I'm going to find the number of moles from the question. I'm going to divide the number of moles by the number of liters, and then I will have the molarity. Okay? Oh. So, moles of iron nitrate equals mass of iron nitrate divided by the formula mass of iron nitrate. You should have picked something easier. We have to figure out what the formula for iron nitrate is before we can know what its formula mass is. Okay? Let's start with the easy part. What is nitrate? What's its formula? There's an N and an O and a 3 and a single negative charge. Okay? Told you in the question that the iron, so if you pick something from group 1, next time pick something easy. Group 1 guarantees it's going to be a +1 ion, cation. Group 2 guarantees it's going to be a 2+ ion. Group 3 guarantees it's going to be a +3. Anything from the middle, they can float. They can be multiple oxidation states, which makes them very, very interesting. An ion can be all sorts of different things. 2 and 3 are very, very common for iron. Let's make this 2. That means I have an iron 2+. What's the chemical formula for iron nitrate then? Because that 2+ and that 1- don't balance. I need 2 of these negatives to balance that. This is going to give me FeNO3, and then everything inside those parentheses is doubled. Going to have to do some adding up. Okay. So the moles of FeNO3 equals the mass of FeNO3 twice, divided by the formula mass of FeNO3 twice. Mass is in the question. Formula mass. Got to go find iron on the periodic table. It's in position 26. It's slap bang in the middle of the periodic table there. And it's, what's that? $55.8. Okay. How many significant figures do I have in my question? Currently, as I see it, I have 3. So I don't need to go into real detail. There's a little decimal, there's a decimal there, which legitimizes that 0. If the decimal's not there, this is only 2 significant figures. Okay. So FeNO3 formula mass is the 55.8 plus this nitrogen twice. Nitrogen is 14 plus these 3 oxygens twice. So that's a 56 plus a 28 plus 6 times 16s. So that's 332s. 96. 96 and 28 is 428 at the 56. 78. 184. What's the actual number? Maybe I got it wrong in my head. What's the actual answer? What's the formula mass of iron nitrate? There you go. So you both agree, which means I'm wrong. I didn't carry something. Divide those 2 numbers. That's the number of moles. What's the number? 0.112. Okay. Anybody disagree? Then we'll continue. All right. So 20 grams of iron nitrate gets dissolved in 250 milliliters of water. You have to find the formula mass, which means the chemical formula. Mass divided by formula mass equals number of moles. We're halfway there. Okay, that's the number of moles. Now, molarity is moles per liter. Number of moles, I just found that, 0.112. And then liters, well, isn't that in the question? Oh, my volume is in milliliters. So I'm going to have to convert that.
Kind of works though, because both are in the 1,000, right?
Both are what?
Oh, once you can run. I'm jumping ahead.
This volume's in milliliters. How many milliliters are in a liter?
1,000.
1,000, so it's 1,000. So all I have to do is figure out, do I multiply that number by 1,000 or do I divide it by 1,000?
Right.
Gonna make the milliliters go away. My conversion factor needs to contain liters and milliliters. If I put milliliters on the bottom, this milliliter and that milliliter cancel. And there are 1,000 milliliters in 1 liter. So I will be dividing that number by 1,000. 0.112 moles divided by 0.250 liters gives you the molarity. Molarity turns out to be what?
It's going to be 2.
That's 0.448.
Capital M is the same as saying moles per liter, okay? The capital M is the same as saying moles per liter. All right, we just found a concentration out of nowhere. Just made it happen. Turn the mass into moles, divide the moles by liters. Got to convert our volume into liters to make that happen. That wasn't particularly difficult, although students do historically start to struggle at this part of the term. All right, here's the follow-on question. There is a part 2. This is part B. We're going to do a dilution. Going to take some volume out of my original solution, put it in a new flask, and then top that flask up, okay? So here we go. My original solution was 250 milliliters, and it was 0.448 moles per liter. I'm going to take something called a pipette, which is just a tube of glass with a bulb in it. And I'm going to remove a volume. How much? I'm going to remove 20 milliliters of that solution. And I'm going to put that 20 milliliters into a new flask. In this flask, I have 20 milliliters of solution. What's its concentration? Yeah, it hasn't changed. I've just changed its vessel. So I know its volume and I know its concentration. Okay, Then I'm going to top it up to a new volume. Goes here. What volume should we top it up to? Has to be a number that's larger than 20. It's a bit too big.
109. 109.
Okay, so now I have 100 milliliters here, but I don't know what its concentration is. Right? I know what it started with. I've put some of it into a new flask and I've diluted it up. I need to find out what the new number is. Here's how we're going to do this. Molarity is moles per liter. If molarity is moles per liter, what is moles?
Master formula.
I like that you came up with that answer quickly, but I want you to rearrange this. Yeah, so take the liters, move it across the equal sign, and it now becomes a numerator instead of a denominator. Okay. Molarity times liter is the number of moles. Let's think. In the whole flask, there was a certain number of moles. But I've taken some of that out and put it in here. So at this point, this first sketch is no longer needed. We don't need this first sketch. We only need this one and that one. The number of moles of iron nitrate that's in here, is it different than the number of moles at the end? No, exactly. It's the same number. Unless you've spilled it, the iron nitrate hasn't gone anywhere. It's just been diluted. So the number of moles at the beginning equals the number of moles at the end. A number of moles is molarity times volume. And I know the molarity, and I know the volume, and I know the volume, but I don't know the molarity. M1, V1, the molarity at the beginning, the volume at the beginning, is equal to M2, V2, the molarity at the end times the volume at the end. Now you would think that those volumes have to be in liters. They should be. But as long as they're the same as each other, they're going to cancel each other out. Because if it's M2 that I need to discover, if M1V1 equals M2V2, what's equal to M2? Exactly. If I move this term across the equal sign, it becomes a denominator. When you move things across the equal sign, they flip from being denominators to numerators. Okay, put the numbers in. If we put the numbers in, that is 0.448 moles per liter times 20 milliliters divided by 100 milliliters. See this? This didn't need to be in liters. As long as the units are the same, they will cancel. That gives me an answer in M. Molarity. What's the answer? 0.098.
Sorry, 896.
Yeah, yeah.
Just misheard you. Anybody else get that number?
Got that.
Okay, then we're good. Before you do, if this is a test, before you go, no, congratulate yourself and then move on. Make sure that makes sense, okay? This is a dilution. You've taken something and dispersed it into a larger volume. This number needs to be smaller than the number you started with. If this number is not smaller than the number that you started with, you multiply it instead of dividing. You've got your terms upside down. So just use a little bit of logic, check your number, move on. Friday, more of these. Let you loose on one, you do one yourself. Them.